Thank you, Ajmiro. Bom dia, good morning. My name is Maurício, as Ajmiro said, and I am professor here at UFRJ. It is our honor to have Professor Venkat Venkatasubramanian in our first Brazilian Congress in Process System Engineering to present the plenary lecture, Artificial Intelligence in Process System Engineering, called Vadis. Professor Venkatasubramanian is with the Department of Chemical Engineering at Columbia University in the city of New York. He earned his PhD in Chemical Engineering at Cornell, Master of Sciences in Physics at Vanderbilt, and Bachelor of Technology in Chemical Engineering at the University of Madras, India. Previously to Columbia, he was a research associate at Carnegie Mellon University and also taught at Purdue University. Our guest has very important research contributions in the areas of process fault diagnosis and risk management, materials discovery analytics, pharmaceutical engineering, and income inequality. Professor Venkatasubramanian received the Norris Shreve Award for Outstanding Teaching in Chemical Engineering 3 times at Purdue University. He won the Computing in Chemical Engineering Award from AICHE, American Institute of Chemical Engineers, and is also a fellow of AICHE. In 2011, the College of Engineering at Purdue University recognized his contributions with the Research Excellence Award. He is also a past president of the Computer Aids for Chemical Engineering, the CASH Corporation. So I'd like to ask you to welcome Professor Venkat Venkatasubramanian.
Can you put this in for my, maybe, can you plug this in for my remote? Good morning, everyone. Thank you very much for that kind introduction, Mauricio. Bom dia. I've learned 2 words in Portuguese, and obrigado. Thanks again, Mauricio, for that kind introduction, and I would like to thank Professor Argimiro Secchi for the kind invitation to present this plenary lecture. I'm delighted to be here. This is my 4th time in Brazil. I love coming back to Brazil, and particularly Rio. My wife and I were here actually a year ago. We spent a few days here, as well as visiting Iguazu Falls. Beautiful country, beautiful people, so I'm delighted to be here. So when Professor Secchi asked me to give this talk, I was thinking of the title, and I decided to give a presentation under this title, Artificial Intelligence in Process Systems Engineering, Quo Vadis. As you know, Quo Vadis in Latin means where are you going? So basically the theme of my talk is where is AI going in process systems engineering, or where's AI going in chemical engineering? So after I made up this title and the abstract and sent it to Argimiro in March, within a week, as it happened, I was visiting Rome to give a talk at the University of Rome. And since I had some extra time, I decided to visit the Appian Way, the famous old Roman road which connected Rome to the rest of Europe. And purely by chance, I ended up visiting this church right at the Appian Way. And it was not on my agenda, it was not planned, it just happened. And this turns out to be the Quo Vadis Church, where St. Peter asked this famous question 2,000 years ago. So I thought it was pretty special that within a week of my making up this title, I actually get to visit the place where these famous words were uttered for the first time. So I thought you might be interested in a little bit of the background of the story. So there is a lot of excitement these days about artificial intelligence, machine learning, Industry 4.0, and some people call it Digital 4.0. This, as you know, is the most recent avatar of this industrial revolution that started some 200 years ago. We had Industry 1.0 at the beginning, which is mechanization of manufacturing. Then came mass production and assembly line manufacturing. Then came the computer-based automation of low-level control, that is Industry 3.0, and now we are at Industry 4.0, which is the automation of the high-level decision-making. Now, this is going to be driven by, as it was mentioned by the earlier speakers, by Internet of Things and artificial intelligence, data science, basically smart and autonomous systems which are powered by data and AI. So this all sounds pretty new, right? But as some of you might know, AI in process systems engineering actually is not new. It has a long history, a 35-year rich history of research and development and implementation in process systems engineering, with more than 3,000 papers published in this area. And so my task here today is to give you, before we answer the question of Vadis, we have to know where we have been before. So I just want to give an overview of what has happened in this field in the last 35 years, and then make some assessment about where we are going in the next, say, 20 years or so. And there are basically three kinds of challenges: conceptual, implementational, and organizational challenges in getting Industry 4.0 or Digital 4.0 done. And the implementational and organizational challenges are very important, but that is the kind of thing that industry tends to worry about. I think the place where academics, students, and faculty can make a huge impact is really at the conceptual level. So my focus of this talk is going to be largely on the conceptual challenges that are ahead. It is a broad overview. I won't go into much of the technical details, but if you are interested in the technical details, I just published a paper in February in ASCHE Journal, which gets into these details much more, and you are welcome to read that. Okay, so let's start with the definition of AI. Now, there are many definitions. I've always found this one to be straightforward, visionary, and simple. This basically says AI is the study of how to make computers do things at which, at the moment, people are better. And there are different sub-areas or disciplines within AI, starting with game-playing programs, symbolic computation, robotics, and so on. But the two areas, expert systems and machine learning, are the two which are of immediate relevance to us in process systems engineering, and that's where the work has been in the past, and that's where the work is going to be largely in the future, and that's what I'm going to talk about. So artificial intelligence basically is about problem solving and decision making under complex situations, and the complexity comes from the following features: the problems are not well defined, or there are model and data uncertainties, very large search spaces, non-linearity, local minima problems, and you require fast answers and so on. But these are the kind of problems that are applicable to many process systems engineering problems, such as in design, control, optimization, risk management. We face these kind of issues there. So some of us thought, why not develop AI-based approaches to these PSE problems in the early 80s? And we expected AI to make a big contribution in the coming years, just as model predictive control and optimization had a huge impact in PSC. But that did not happen. The impact of AI in those early years, or until now actually, has not been that much. So what went wrong? Why wasn't there any impact? So before I answer that question, I would like to basically review the different phases of AI in chemical engineering as I classify them. So the first phase of AI, which I call as the expert systems era, that started in early 80s and went on through the 90s mostly. And this is based on this kind of an architecture of a computer system. So the idea was to develop a computer program that mimicked human experts' problem solving in a particular domain, such as medical diagnosis. How does a doctor go about perform her diagnosis? So can we capture that reasoning in a computer program? And so people came up with this architecture of representing domain knowledge in a knowledge base, an inference engine which uses that knowledge and does the reasoning and then communicates the decisions to the user. And this is based on 4 key important ideas. One is the separation of the domain knowledge from inference, this split. And then the flexible execution of the program order, and this was very important for problems such as diagnosis. Then the if-then representation of the rules, which is how we typically carry knowledge around in our minds. And then finally, semantic networks for organizing knowledge, which is in the form of objects and their properties, and then classes and subclasses, and so on. So these important breakthroughs came in the 70s, and they got implemented in the late 70s and early 80s. And the first expert system was developed at Stanford, MySyn, which is an expert system for medical diagnosis, and that was developed by Stanford computer scientists in collaboration with Stanford Medical School faculty. And it was for diagnosing infectious diseases. And it took about 10 years and a few $1 million to develop the system, but it was very impressive when it was finally done. It had the knowledge of 6 board-certified MDs. So it was actually better than any of the doctors who were consulted to develop this system. So this was a very impressive progress. And this inspired a whole bunch of activity in engineering, particularly in chemical engineering. Starting with the expert system Confide. That's the first one that was developed in chemical engineering at Carnegie Mellon, where your next speaker tomorrow, Professor Yu, graduated from. And this was the work of Art Westerberg and his graduate student, Rene Benyares Alcantara, who developed this system for thermodynamic property prediction for complex mixtures. Then Rene went on to develop Decade, also working with Westerberg for his PhD thesis, and this is a catalyst design system. Around the same time, I was setting up my AI work at Columbia, and we did some work on developing model-based diagnostic system for chemical processes. And around the same time, George Stephanopoulos was setting up his AI effort at MIT, and did pioneering work on expert system approaches to modeling as well as design. And Jim Davis did his work on distillation column design at Ohio State. The first course in artificial intelligence and chemical engineering was developed and taught at Columbia in 1986. And the first conference on AI in chemical engineering also was from that area in 1987. So there was all this excitement and all these initial and promising efforts that happened at the time. But expert systems had a couple of important drawbacks. One is it just took too much time, effort, and money to develop these systems. And it required specialized expertise and working with Lisp as the language, which is a great language, but not very easy to work with. And so as a result, this does not scale that well for industrial applications. So that was the first phase of AI in chemical engineering. So as the interest in expert systems was waning, another technique was gaining popularity in artificial intelligence at the time, and that is basically neural networks. So I call this the second phase of AI, which is machine learning using neural networks. And the key ideas here were the rediscovery of the backpropagation algorithm, where using these networks automatically discovered the knowledge or the correlations hidden in the data by themselves. And this is a bottom-up strategy, as opposed to the expert system strategy, which is top-down, where you had to put the knowledge into the system. Here, the system automatically discovered the knowledge on its own, working with lots of data. And this made the scaling problem a lot easier. That means now you could field these applications much more easily. And also the other excitement about neural networks was it was able to do nonlinear function approximation problems, such as this, as well as nonlinear pattern classification problems. So as a result, there was a lot of work done in chemical engineering in that decade. At that time, mostly on fault diagnosis and process control applications of neural networks. Okay, so from this era, I just want to highlight three or four important advances that was made, which are relevant to our present discussion about how AI fits into chemical engineering and where AI is going. One is this ASM consortium that was started in 1995 by Honeywell. This was a consortium of all the leading oil companies in the US at the time, including Exxon and Mobil. There were two different companies at the time. And, the goal of this project was to develop the next generation control system for chemical plants. And so this, we called it as intelligent control. That is, it will make high-level decisions on its own. Typically, we depend on operators to make those decisions. Can we get computers using AI make those kind of decisions, such as interpreting alarms and diagnosing faults and making appropriate control actions at the supervisory level. This was funded at a level of $17 million. Half of the money came from the US government, and the other half came from the contributions from these participating oil companies. There were 3 university groups involved. One was the group of Jim Davis at Ohio State, then my group from Purdue. I was teaching at Purdue University at the time. And the third one was Kim Vincente from Toronto. This program is actually the forerunner to the Smart Manufacturing Initiative that got funded 3 years ago. And if you look at the goals of this new program, Smart Manufacturing Initiative, it is essentially the same things that we tried to do 25 years ago. And turns out we were just too early, as I'll mention again. So one of the things I want to highlight from this work was the system that we developed at Purdue called Diagnostic Toolkit. And this one is an expert system architecture which had a bunch of modules. Each one looked at real-time process data and independently made an assessment about whether the process is functioning normally or abnormally. And if it is abnormal, what is wrong and what to do about it, and make that recommendation to the scheduler, which then built a consensus assessment about the process and then communicated to the operator. So this involved monitoring trends and recognizing abnormal trends and then signaling to the operator, as well as it had hybrid models building causal knowledge in the form of diagrams here with principal component analysis on the other side. And so this system was implemented in an expert system environment called G2, and it was tested at the Exxon's plant, chemical plant at Baton Rouge, Louisiana. So it was tested using real-time data, and the system performed very well. It successfully diagnosed many faults, half an hour to 2 hours before even the alarms went off. So even before the operators knew something was wrong with the plant, the system recognized it and then diagnosed it and then communicated to the operator on many different failures. So people got really excited about this performance, and so Honeywell actually licensed this technology from us in 1998, so that was 20 years ago, in order to make commercial product which can then be sold to various companies. So what happened? Well, beyond the research prototype, Honeywell discovered that it was very difficult to scale these systems using the technologies that were available to us at that time for practical implementation. So this is where we ran into implementation challenges and organizational challenges. So we knew how to solve this problem. We simply couldn't scale. So looking back in retrospect, I think that we were just 20 to 30 years too early to attack this problem from an industrial point of view. From a conceptual point of view, we were able to do that, but we couldn't get it working in an industrial setting for reasons I will explain in the next few slides. Now let me change direction a little bit and talk about a different application. Now this is in materials science, where you want to design a new material which satisfies some properties that you have. And in order to do that, you really have to solve two problems. One is what I call as the forward problem. That is, given the structure, can I predict the properties? And the design problem is the inverse problem. That is, I know what I want, but I don't know what structure or formulation will give me that. And so we developed a hybrid neural network approach for this, which had first principles knowledge combined with neural networks. So it is a hybrid model for the forward problem. And the inverse problem we solved using genetic algorithms, what is known as directed evolution these days. So this actually generated a lot of excitement in those days. It was even written up in the popular press. Dallas Morning News actually carried a couple of articles about this, and this was 25 years ago, 1995. And we went ahead and designed fuel additives for Lubrizol using this approach, and rubber compounds formulation for Caterpillar. So the system was able to discover new materials in a matter of hours. And typically, at that time, it took expert designers in these companies weeks to months to come up with a new fuel additive or a new rubber compound formulation. So this was an industrial result. So this, we got pretty excited about this. And it turns out at the same time, Professor Frances Arnold at Caltech, another chemical engineer, had independently arrived at this genetic algorithm-based design, but she was using it to design enzymes in vitro. So we were using our approach to design polymeric materials in silico, in computers, whereas she was designing enzymes in vitro. And this turned out to be a very important idea, not because I say so, it's because last year the Nobel Committee said so, and Frances Arnold received the Nobel Prize in chemistry for this work of directed evolution. Now, another important advance from that period, and this was work we did for ExxonMobil in around 2002, where it was developing an AI-based modeling environment for catalyst design. And we called it Reaction Modeling Suite, where in designing a catalyst, one of the problems you have is to discover, you have to understand the underlying microkinetic reaction network that takes place on the surface of a catalyst. And you could have typically dozens to hundreds of chemical species involved. And so to develop a mathematical model for them, you'll have dozens to hundreds of differential and algebraic equations. And all these things typically take weeks, if not months, to develop and test and make predictions and so on. So we developed this system in order to reduce the modeling time from weeks and months to hours. And that required developing a new kind of a compiler dedicated for chemistry, and a new language for representing now, chemistry rules, and a new ontology for organizing chemistry knowledge, and a new learning system. So for example, the system knew about different kinds of reactions that can take place on the surface of a catalyst. This is basically how bonds form and break on the surface of a catalyst. Could be alkane adsorption, desorption, carbonium ion proteolysis, and so on and so forth. There are about 10 different such classes. And these were represented in these special language, which we developed for representing chemistry, that get automatically converted into reaction, microkinetic reaction details. So you form the reaction network, and from that, this model, mathematical model, is automatically generated, then you solve, and so on and so forth. So this cut down the time that used to take weeks and months to do this to a matter of hours, and now if the same system, if we were to do it all over again, you could do this in real time because of all the progress that has happened in the last 20 years. And so we proposed an iterative approach for this model refinement. So the way it would work is a human expert would initially propose what kind of hypothesis might be driving this particular reaction, and the reaction modeling suite will convert all those things and make predictions, and then you compare, and if things are not working well, you go back and refine your hypothesis. So the bottom cycle is about refining the model, and the top cycle basically will tell you where new experiments need to be done in order to acquire data to test this model. So this is basically, the top cycle is doing guided experimental design, and the bottom half is doing guided model development. And so this we proposed in 2003. And it turns out computer scientists in the last 5 years have rediscovered this approach, and they are calling it active learning. So all these things tell you that there was actually very good progress that was made on developing AI methods to various problems in process systems engineering, for design, control, optimization, safety analysis, scheduling, pretty much the entire spectrum of PSE. There were proof of concept systems developed. In some cases, even industrial implementations were also executed. So if that is the case, how come then AI did not succeed as well as it should have? Okay, because we made all this great progress on the conceptual issues. Well, it turned out we suffered from a lot of these practical problems. These are the implementational and organizational problems. Basically, there was a lack of computational hardware. The software was not as good as what we have now. Communication infrastructure was pretty much absent. There were no dedicated hardware such as GPUs at the time. Data was limited in those years, and whatever we had, all those things were very expensive. And also, people did not trust computer-based recommendations that much in those days. I'm talking, some 20, 25 years ago. So basically, it just took too much effort, time, and money to develop AI-based solutions for industrial applications. And as I said, looking back, we are about 20 to 30 years too early. So are things different now? Okay. I believe they are different for the following reason. In 1985, just about the time when I got started doing AI at Columbia University, the greatest computer we all wanted to get our hands on was the supercomputer called Cray 2. And it was a huge beast. It took up an entire floor of a building. It required about a dozen people to run it, to operate it, and you can see, right, sorry. So you can see there are people there, and then you can see all the, this is the Cray 2, and this is all the support hardware, and it consumed a lot of power, 150,000 watts. So it generated so much heat that you needed some powerful air conditioning system to make this thing work. I used to joke that Cray was really a space heater which did computing on the side. And then it cost $16 million in those days, $32 million today. So what would Cray look like today? Okay, so this was some 30 years ago. What would Cray look like today? I'll show you Cray. My Apple Watch. Apple Watch, in fact, is actually more powerful than Cray in all those metrics. And not only that, it just consumes 1 watt of power, and it's about $300. If somebody had told me in 1985, Venkat, in about 30 years, you'll be wearing, not only you will own a Cray yourself, you will actually wear it on your wrist, I would have laughed. Everyone would have laughed. You would have said that guy is completely insane. But that's basically what has happened. So that is a 150,000-fold increase in computing performance per unit cost. This is a game changer. This is what is different now. And this is why AI, I think this time around, is going to have a huge impact. Okay? So how did this happen? Well, if you really drill down to this, I think you can trace it to just one single thing, which caused all this. It's basically Moore's Law. Gordon Moore, one of the co-founders of Intel, in the 1960s made a prediction that every 2 years, the number of transistors we'll be able to pack in a chip will double at the same cost. And so he said every 2 years we'll be doubling, and he thought this would go on for maybe 10 years. Much to Moore's surprise and everyone else's surprise, this thing called Moore's Law not only delivered that kind of doubling every 2 years for 10 years, it did that for 50 years. So 50 years of this doubling compounding is the reason, if you actually do the math, you'll see that that gives you Cray at $300. So this all happened because of Moore's Law. It just happened that we were able to pack more and more transistors. And basically, that's the Moore's Law trend. And so this progress in hardware gave birth to a lot of other ancillary benefits, such as the computational power and storage became cheaper. Great languages arrived, such as Python and Julia. These languages they can't be here. All those libraries can't be here if we didn't have the hardware to support them. So this gave birth to software progress. This gave birth to communication infrastructure. Internet and wireless wouldn't be here if Moore's Law were not to be true. And because of all that, we were also gathering more data. We wouldn't have big data without Moore's Law. And as a result, computers have become much more a part of our daily lives, and we trust computer advice much more these days. We take recommendations from Google, Yelp, and when you want to watch a movie, you check with Rotten Tomatoes. If you want to date, you look up Tinder. And so people trust computer advice a lot more than 25 years ago when we tried to give this thing to operators. There was a lot of resistance. Now, there is still some resistance, certainly in industrial setting, but it is a lot less. So basically, what has happened is it's become a lot cheaper and easier to do AI now, and that's mostly because of Moore's Law, and that is why I'm excited about what is happening right now. So this brings us to the new phase of AI, phase 3, and this is the data science phase, or the machine learning 2 in my mind. And this is driven by 3 important ideas: convolution and deep neural networks, reinforcement learning, and statistical machine learning, such as Bayesian learning, and so on. Now, these are important ideas, but they are really not new ideas, as you will see in the next few slides. What is new is we have more data, faster computers, better languages, and then all these things are much cheaper. And this is what is behind all the progress in natural language processing, computer vision, robotics. So this is what is giving us Watson, Siri, Alexa, AlphaGo, self-driving cars. All those things are because of this progress. Now, there is a lot of hype surrounding AI and machine learning now, just like there was a lot of hype in the first phase with expert systems. I remember those days. There was a lot of hype with neural networks in the 90s. I remember those days as well. And similarly, there is a lot of hype around this time. And so it's important to take a reality check and draw a distinction between what is a fantasy and what is more realistic. First of all, a lot of the things that you hear as new ideas, they're really not new. Like I mentioned, many of them are 20 to 30 years old. And in fact, many of the things that people claim to do now were demonstrated a long time ago, including self-driving cars. The self-driving car was first demonstrated in 1995 at Carnegie Mellon in a project called Look Ma No Hands. These are the guys, that's the name of, they come up with cute names, don't they? So Look Ma No Hands project where this Dodge minivan drove itself from Pittsburgh to San Diego, most of the distance, 2,800 out of the 2,850 miles. And this was 1995, 25 years ago, self-driving car technology was demonstrated. So self-driving car idea is not all that new. People did it at Carnegie Mellon, they did this. What is new is that was a several $million vehicle funded by the US Defense Agency, DARPA. Now, you could do this for a few $1,000s, maybe $10,000 worth of technology in there. So the price has crashed. And secondly, the reliability has gone up. And thirdly, you could fit this car in a small, like a Volkswagen Bug kind of thing. The reason it was a Dodge minivan, because they needed the space to pack all the computing equipment. And that size has shrunk now. And so that's self-driving cars. The convolutional neural networks, which everyone is excited about, which is behind all this image recognition and speech understanding and AlphaGo for that matter, that idea goes back to 1990. That's when the first paper was published. Autoencoder networks, another great exciting breakthrough, was actually published in 1991 by a chemical engineer. Mark Kramer, who was an assistant professor of chemical engineering at MIT, published this paper in AICHE journal, not in a computer science journal, in a chemical engineering journal. And it was rediscovered by computer scientists 20 years later. Like I said, the inverse design of materials that everyone is excited about now, we demonstrated this in the early 90s. Causal models and explainable AI, some of the early work was done again in the early 90s. And hybrid models we demonstrated in 1995. So for the younger people here, the students particularly, I think it is worth reading all the old papers because there are some really neat ideas in there. They were just far ahead of their time, and that's why they were not recognized at the time. So the second one is you don't need convolutional neural net and reinforcement learning for all problems in chemical engineering. They are appropriate for certain classes of problems, such as in vision and speech understanding, and some applications in chemical engineering would need them, but not all of them need them. Many of the problems in chemical engineering, whether it is in design, control, optimization, and fault diagnosis, can be actually handled using the techniques, the older techniques, which we demonstrated in phase 1 and phase 2. They are a lot easier to use, and they are a lot easier to understand these days compared to what it was in those years. And the third one is that often we actually know a lot about our underlying materials, systems, and processes in chemical engineering. We are not completely clueless about what is going on. There is a lot of physics and chemistry that we know about it. There is a lot of prior knowledge. So how do you actually leverage that using data science? I think this is one of the most important challenges facing us. And in that sense, chemical engineering is very different from game-playing programs or vision. For example, recognizing a cat from a dog, as impressive as it might be, there's no underlying physics and chemistry behind it. There's no underlying, fundamental laws. A cat, why is a cat different from a dog? Well, that looks like a cat and this looks like a dog, and that's about the explanation. Whereas, in chemical engineering, when you propose a particular catalyst or a particular diagnosis, for example, you want to know why the system recommended this particular failure as the source of this symptom and not something else. That explanation capability is completely missing in the current AI systems, and that is an important area of research for us. So there is a celebrated example in data mining where when Osco Drug, this is a big departmental store in the US, as you know, when they analyzed point of sale data, that is customers buying stuff, when they analyzed that data, they discovered that people who bought diaper also bought beer. Okay? I mean, you can imagine the situation, right? I mean, it's probably, late at night, 7, 9 o'clock, 10 o'clock, suddenly you discover you're out of diaper, you send the guy out, go get some diaper, and, he goes there complaining, but then one is there, he says, well, I might as well pick up some beer. So, Oscar discovered this through data mining, and they put this to use. So they arranged for these diapers and beer to be located in such a way that it improved the sales and they made money. They didn't particularly care why this happened. They were happy to see the result and make money from it. But in chemical engineering, if we are told that this particular catalyst improves yield or selectivity, we want to know why. We want to know the underlying mechanistic understanding of what happened. Because there are no fundamental laws behind diaper-beer correlation, but there are fundamental physics and chemistry-based laws behind all the systems and processes that we work with. So mechanism-based causal explanation is at the foundations of science and engineering, and so it is important to be able to do that. For example, hammering this point some more, a self-driving car may drive itself very impressively through, say, Manhattan, where I live, and probably will do a better job than most New York drivers, okay? But does it understand the Newton's second law, or the concept of mass, acceleration, momentum, and velocity, and so on? It doesn't, okay? Whereas we do. It's, in some sense, its behavior is like that of a cheetah chasing a deer in the wild that you see in National Geographic channels on TV, right? Both animals display an amazing mastery of the dynamics of the chase, but they are completely clueless about the underlying physics, which is Newton's laws, or the underlying math, which is calculus. Whereas humans understand that. We may not run as well as a cheetah, but we certainly can understand the underlying physics and math of this. So this is the problem. Current AI systems, in my mind, they have achieved animal-like mastery of their tasks. They know what to do and how to do it and how to do it well, but they have no understanding of what is really going on, just like an animal. And so this is a major problem, I think. A mechanistic causal understanding is very important for this AI systems to be accepted much more readily. Particularly, it is important for safety critical applications in our industry, in diagnosis, control, and process safety analysis. We really need our AI systems to not only know what to do, but why they are doing it. So how do we get AI to learn that? And that is a huge challenge, not in chemical engineering, actually in AI. And we are right at the intersection of that. So going forward, I classify the kind of problems that we face into three broad categories. The first one, these are relatively easy applications of AI. This is where you have large amounts of data, and then there are easy to use machine learning packages that are available on the internet, Keras and TensorFlow and whatnot, various Python libraries. So these are routine applications. They can be done now, and in fact, they are being done now as we speak. And just to give you some examples, these are, recent published work on process operations, for example, oil well performance monitoring implemented already by oil companies, wind turbines monitoring, and for efficient power usage, process intensification, preventive maintenance, scheduling maintenance before equipment, fails, so that you manage downtime much more effectively. In material science, estimating physical properties from structure, or going the other way around, nanoparticle packing, reaction path prediction. These are all relatively easy problems to solve. If you have lots of data, we know how to do these things. We knew how to do these things 20 years ago, 30 years ago. We actually demonstrated these things. And there is a lot of value in doing this, particularly in an industrial setting, and that's okay. And these are the relatively easy problems. The really important and challenging problems are in the next two categories. The hard problems of AI are building first principles understanding into our AI models. How do you build physics and chemistry into it? For example, this figure shows how the fundamental properties of molecules based on physics and chemistry can be used to infer descriptors, which are then correlated with neural networks and so on. This is the kind of approach we used in designing fuel additives. Building causal models is another such challenge. Here is an example of combining that with signed diagrams. And to do these kind of things well, I think it will take another 10, 12 years. Some existence proofs have been demonstrated, proof of concept have been demonstrated, but to do these things routinely and easily and reliably and systematically, I think we are still about 10 to 12 years into the future, and this is where further research is needed, particularly in universities. Harder still are building IBM Watson-like systems for process systems engineering applications. This is where building ontologies such as this kind of an organization, or these special purpose languages and compilers, as I showed for the reaction modeling suite, that's still 10 to 20 years away. These are much harder problems, and these things won't happen by simply taking some program from the internet and then letting it loose on your data. But these are important problems which we really need to solve to do design control optimization, all those things, diagnosis well in systems engineering. These are the challenging problems. So my appeal to the young people in the audience, particularly the students and postdocs and younger faculty, is we really need to focus on the hard and harder problems. The easy problems, anyone can do it. It doesn't require a whole lot of creativity. And it's already happening anyway. Where you can add value, where we need that progress, is in solving these hard problems and harder problems, where we build in fundamental knowledge into these systems and then make these AI systems much more reliable for various tasks. So just talking about this such systems, what would it take to develop a Watson-like system for chemical engineering application? As impressive as Watson was, this particular Watson for PSE is a lot more challenging because we are not just dealing with qualitative facts. Now you have quantitative information, mathematical models, charts, tables, spectra, and heuristic knowledge, and so on. So this is what we attempted to do some 10 years ago when I was still at Purdue in designing a Watson-like system for a pharmaceutical manufacturing application. So this is a system which had a whole bunch of knowledge about models. It had experimental data. It had material science models, as well as various tools for design and manufacturing. All these things are organized behind this ontology. But as a user, you don't see any of these things. They are all hidden behind you. And so you see this kind of a system before you. And let's say that the recent manufacture, the recent batch of tablets you are manufacturing had some dissolution problems. Now, this is a big problem in the pharma industry, as you know. If the tablets don't dissolve in water, then they're not going to work that well inside you. And so this is a huge headache. So you get this problem, so you're trying to find out what went wrong and what to do about it. So you go ahead and pull up the data and compare it with the model, and you see that the model, the blue curve, seems to do well initially, but then the data model don't agree later on. So you wonder whether some of the assumptions have been violated. So you go back and check your model, but then that was developed 5 years ago, and the guy who developed it is gone. But thankfully, that information is here in this Watson-like system. So you go back and check your digital and discrete event simulation models to see whether these assumptions are true, and even go back 10 years to your eLab notebook to see the original experiments, even compare crystal structure for the API, and so on. So you're able to pull all this information in real time and then diagnose what went wrong and fix it so that the next batch of tablets will be appropriately produced. And this required organizing knowledge in an ontology which was created for the first time for pharmaceutical engineering, Purdue Ontology for Pharmaceutical Engineering, which had knowledge about various decisions that are made, structure about the various chemical and physical properties of the pharmaceutical materials, mathematical models and computational tools like Mathematica and MATLAB and so on. And for this, we created an ontology called OntoModel, where the same equipment, which this is the roller compaction, it can be modeled as a neural network or as a discrete event simulator, a stochastic model, or based on first principles using algebraic and differential equations. So how do you develop all these things and then keep them all speaking to each other? This interoperability is a huge issue in implementing AI in Industry 4.0. And then this required developing an ontology which classified different kinds of models and the assumptions. All these things are made explicit. And so when you try to use this model, you know what it is good for and where it can be used and where it should not be used, and so on. So let me summarize all the things I've said quickly. We have already gone through two phases of AI. The expert systems phase in the early 80s, the neural networks in the 90s, and now in the new exciting phase of data science. And what is new, as I said, is data, hardware, and software. It is in that order of importance. What is new is, why is AI possible now? And it's making more inroads is because we have lots of data, we have much better hardware, we have much better software, and all these things are relatively cheaply available. There has not been that much progress in algorithms per se. The algorithms are all 20, 30 years old. So what is really new are these three things: data, hardware, and software. And from a conceptual point of view, I think there have been three major revolutions, major paradigm shifts in modeling knowledge in chemical engineering and in process systems engineering in the history of our field. As you know, chemical engineering for a long time was an empirical field. People collected lots of data. We were building chemical plants 100 years ago, 150 years ago with the Solvay process in the 1850s and so on. Long before process systems engineering was known, long before mathematical models were developed, people were still, they were using reactors and distillation columns. It was a highly empirical field. That changed in the 1950s and 60s through the work of Neil Amundsen, who was a professor of chemical engineering at Minnesota, who brought in techniques from applied mathematics to develop first principles-based models of chemical engineering unit operations. And so he brought in techniques from linear algebra, differential equations, ordinary differential equations, partial differential equations, and so on. And so that is the first paradigm of modeling knowledge in chemical engineering. I call this the Amundsen era. Okay, so the idea was to model process units from first principles. The second revolution came, the second paradigm shift came through the work of Roger Sargent at Imperial College and their descendants. And what Roger did was to bring in ideas from optimization into chemical engineering, mathematical programming, mathematical optimization. And so this is to model decision-making formally. Decision-making until that time was heuristic, was informal, just like in this case, chemical engineering was informal, process systems engineering was heuristic. And that became formalized through the work of Roger Sargent and his students, such as Ignacio Grossman, and whose student is Professor Fengqi Yu, who's going to talk to you tomorrow. And so largely this is about how to model constraints. In a similar way, I think we are in the third wave now, in the third revolution in knowledge modeling, in the third paradigm, and that is bringing in artificial intelligence techniques and concepts into chemical engineering. It didn't start recently, it actually started in the 80s under the leadership of Art Westerberg, George Stephanopoulos, and others from that era. And again, this is about bringing formal techniques to model and data in decision making. But what is new here is modeling symbolic structures and symbolic relationships. So this is where and how AI fits into chemical engineering. Initially, we brought in techniques from applied math, then we brought in techniques from optimization, now we are bringing in techniques from AI, and this is all to model the knowledge in chemical engineering. This was to model knowledge about process units. This is about modeling knowledge about process engineers. And so, as I mentioned, I see there are three categories of problems: the easy, hard, and harder. And the easy ones people are already doing. And I think that as academics, we should really focus on these hard and harder problems. This is where innovative and creative energies are required. This is where the really intellectually challenging problems are, which is about how to build in first principles knowledge into data science techniques, as well as how to build these domain-specific ontologies and languages and compilers which are required for the really difficult problems in design, control, optimization, fault diagnosis, safety analysis, and so on. So with that, let me acknowledge dozens of students and postdocs who have worked with me over the years. It is their work that I am actually presenting to you today, and as well as my collaborators from the Purdue days and a number of funding agencies. And obrigado, and I will be happy to take any questions you might have. Thank you.
Thank you, Professor Venkat. I'd like to know if there are questions. We have time for about 2 questions, I think. Yes?
Well, hello. I'd like to present myself. I am Ricardo Pontes. I'm a professor at the Federal University of São Paulo. I teach basically simulation and process projects. And actually, I will have 2 questions for you, Professor. And first, I would like to compliment on the very enlightening presentation that you just gave us.
Thank you.
Okay. First question. You mentioned that we chemical engineers sometimes we have the curiosity to question results given by a computer, by AI. Okay. And I see this as a trend for those above 40. Maybe not the new generation. How do we, as professors, as educators, can still, on this new era of AI, instigate students, new engineers, to always question those solutions? Okay. Second question I would like is...
Can I answer the first question first?
Sure,
because
sure, then I will.
By the time you ask your second question, I might forget what you asked first.
Sorry.
That's a very good question, and in fact, I myself teach design and control. I taught that at Purdue, and I teach at Columbia. And I see that kind of behavior all the time. People would come to me with a distillation column that's 500 feet tall. And I asked them, do you think this is reasonable? They would say, no, this is what Aspen said, And so your point is, absolutely important, that there is a tendency to accept whatever the computer gives as gospel, and not question it. And that is something we really, as professors, as educators, we really need to drill this down, that you really have to ask whether this makes sense and why this is the result. And in that sense, we should encourage our people to make back of the envelope, analysis and estimates about what it should look like, so that we can understand whether the computer is making the right recommendation or not. And I think there is a tendency to believe in the computer a lot more, certainly among the younger people, because in their experiences, generally speaking, whatever the computer recommended seemed to make sense in day-to-day experiences. And that might be okay, but in engineering, the cost of a mistake is very high. So this is what I tell my students and my children, that when Rotten Tomatoes makes a movie recommendation and you see it and you are not happy about the movie, it's okay, you wasted 2 hours, maybe $10. So the cost of a mistake there is low. But if it makes a recommendation with respect to process safety in process control applications and you get it wrong, the cost of the mistake in a chemical plant can be very high. And so that makes AI systems a lot more suspect. It's one thing to use AI for hotel recommendations and TripAdvisor and so on. It's an entirely different game when it comes to design control optimization and safety in chemical plants, where you really need to know why that recommendation was made and whether that we should question those recommendations, because the cost of a mistake can be very high. So I share your concern about this, and it is important for us as professors to instill this kind of thinking in the younger students we teach.
Thank you. And this brings me also to the second question, okay? And you see, you brought to us information and trends that more and more decision-making will be done by AI, or at least not decision-making, but choices given to those who have to make decisions.
Right.
And as a former project engineer, my concern is that some of these students, okay, I'm not criticizing all of them, okay, but some of them might be maybe 10 years from now, skipping maybe in a project, FEL 1, FEL 2, going straight to basic design without giving too much thought on conceptual design. And this is where you lose all that money, okay, because you just accept everything on the computer. And my question is, how do we, as users of artificial intelligence, let's take some of the responsibility given to AI and say, this has to be decided by humans still. This cannot be skipped, and this will take some time to do. Like, we shouldn't let still some computer make a decision which free technologies might be used to produce a certain product.
Right,
Okay?
right.
I don't know if you understood my question.
Let me answer the way I understood it. Okay. And it is related to your first point, isn't it? It's, that is, whether we should trust computer advice blindly. And as people rely more and more on AI for these decisions, they will be losing these skills themselves. And then when it comes to a critical point, they may not have the experience that is needed to address those things, whether it is in design, as you pointed out, the design options, or even in operations when the alarms go off. And it is not clear, at least in my mind, where to draw that line. I mean, like you said, there should be some sort of a demarcation between for what things we depend on the computer as the responsible agent, and then for what things we depend on the humans. I think we will learn all that in the next 20 years. As these things become more and more widely used, we make our mistakes and then hopefully learn from those failures. And, but keeping an eye open that there is this possibility that there are certain things, in my mind, I mean, next 30 years, at least in chemical engineering, in process systems engineering, humans are not going to go away. The problems are so complicated, and the human presence will be needed. We will get a lot of assistance. These AI systems, in my mind, will serve as smart assistants, but the ultimate decision-making authority will still stay with the humans, and the responsibility also should stay with the humans for the foreseeable future. Too much reliance on computers can be problematic at this stage. We are not there yet. And a case in point is what we saw with the Boeing MAX accidents, right? So that was computer control failure, and then, in fact, it's a failure in design, I would argue. This one particular sensor was largely deciding whether whether the plane was stalling or not. And you can see there the trade-off between efficiency and robustness. As you drive our systems to be more and more efficient, there is a cost to be paid. Even though you're saving money clearly by increasing the efficiency, the cost will be paid in the robustness. That your system will not be as robust as it could be. So at some point we have to, it is related to your question about where to draw the line. It is the same trade-off between efficiency and robustness. Robust systems would require fairly active human involvement, even though it is costly in the short term, but it actually is safe, it saves money in the long run. For example, now Boeing is going to pay billions of dollars for these 2 accidents that happened. Sure, they saved money with these more efficient design in the short term, but there is a cost in the long term if you make that, if you cross the line too far to the other side. Both questions are very difficult questions to answer, and but these are the things we need to keep in mind as we teach our students. Thank you.
Thank you.
Hi, thank you for your presentation, Professor. I'm João Bruno. I work for Senai Innovation Institute, located in Rio de Janeiro, and I'm also a PhD student here in the university. You presented that AI can be easily applied in process intensification. And process intensification is very important because it has, it can impact a lot the chemical industry. So can you give us some examples or suggestions about how can AI be applied in process intensification?
It really, I don't think there is a single unified approach. There might be in a few years' time. We are still learning and exploring these things, right? I mean, so it varies from a chemical plant to a petroleum refinery, whether it is offshore or onshore. So all those contexts matter, and whether you're trying to improve the performance of a distillation column versus a reactor versus a heat exchanger versus tower. All those things, those kind of specifics do matter. But when I said they are easy problems, the operative word also relatively easy problems, in the sense they are easier than the hard and harder problems, as I mentioned. And the key thing here is it's how much data you have. If you have lots of data and the data is in good shape, they are curated well, and they can be correlated with tags and so on, then there is there are things which you can use to extract much tighter operating regimes where you can save on efficiency or improve the yield and selectivity, those kind of performance categories. I cannot reveal the names of these companies, but I've spoken to several oil companies and leading chemical companies in the US, as well as vendors like Aspen Tech, where they tell me that typically various neural network-based process intensification applications are already happening, are already being implemented. And so, and the common feature of all these things is they have lots of data. There are lots of data, and also they can transfer the data from one system to another system. This interoperability turns out to be a big headache in many of these things, because the control system may be using Emerson, and your scheduler may be using Oracle or SAS or something. So how do you get all these data to talk to each other is actually much more of a headache than the AI itself. So it's, in some sense, it's more of an IT problem than an AI problem. And so that's why it is context specific.
Good morning.
Good morning.
I have been reading your work about statistical teleodynamics and purpose-driven systems modeling and emergence. And I'm very impressed by the conceptual insights I found there. For example, interpreting entropy as fairness and not disorder. Disorder always annoyed me. In my opinion, the ideas you proposed have the potential to revolutionize areas as a part of the systems engineering, artificial intelligence, economics, and philosophy. Recently, I showed your paper to a friend of mine who is a student of economics, and he too was very impressed. My question is, do you have ideas in order to improve the communication between the fields and spread your theory? And how can you present systems theory and statistical teleodynamics for philosophers and economists, for example? And if we can do it, do you think this kind of knowledge can be used by policymakers to improve social conditions in countries so unfair as Brazil, for example? Okay,
thank you very much. What he is referring to is some work which I didn't talk about today. I recently published a book on economics, on income inequality, where I modeled a society, a democratic capitalist society, as a dynamical system. So it goes back to a question I asked myself some 20 years ago. If I'm a systems engineer, I do design, control, optimization of chemical plants for a living. But if someone were to ask me, can you design me a society from a systems engineering perspective, what would that approach look like? So I started working on this on the side, more as out of, as a hobby, as a passion, as a side interest. I didn't expect this thing to go anywhere. Much to my shock, it actually went somewhere. And it ended up in this book that got published 2 years ago. So where it is a systems engineer's view of how to organize a society so that we have fair and equitable income distributions. And I call this theory statistical teleodynamics. Telos in Greek means goal-seeking. And since people are goal-seeking individuals, this is the dynamics of people, so it's called statistical teleodynamics. And if you make these agents dumb like molecules, you get all of statistical thermodynamics back as a special case. And so what that gentleman is referring to is that work, and it's an entirely different seminar. I'll be happy to come back to Rio and give that again. But very quickly, this is a completely new view of economics. Neoclassical economics, as you know, is largely based on ideas from classical mechanics. That's why they use concepts like equilibrium is when supply and demand forces balance each other. That whole idea of forces balancing each other is a classical mechanics idea, which was borrowed into economics. And whereas we know that a free market is actually a dynamical system with millions of people buying and selling their services. So if you're going to borrow ideas from physics, it should be statistical physics, and the equilibrium should be statistical equilibrium. But then you run into some trouble with entropy, which is what he referred to. So I kind of sorted these problems out. So it casts economics on a statistical mechanics foundation as opposed to classical mechanics foundation. And one of the surprising outcome is it is able to answer a very old question in economics, which is how much income inequality is fair? This is a question which Adam Smith worried about. And for 200 years, this has been an open question. Using my theory, I'm able to answer that. And it turns out a log normal distribution is the fairest way of distributing income in a free market society. And so that can be used for guiding policymakers and so on, but we are still far away from people taking these things seriously and doing something about it. But thank you for that question, though.